Dear friends, welcome to this course Story of Photoelectric Effect. As the name indicates, it's not a course in its regular sense. We will not have much of examinations and gradations and telling who has done performed well and who has not performed well and all those things. We will not be doing that. It is just a story. And I have chosen this photoelectric effect, telling stories of photoelectric effect because a very special timing. We are in 2021. It's very turmoil everywhere because of the health problems and virus problems and all those things. And it seems that life is very different from what it used to be and very difficult also. But at the same time, those who have fought well with this virus and are still in a good spirit, they have the opportunity to explore newer things because you don't have those compulsions of regular fast life for your occupation and all those things. So this is one. And then this is a centenary year of Einstein getting Nobel Prize. This Nobel Prize in Physics 1921 was given to Einstein, and it's a common knowledge that Einstein had done a lot of work on relativity and Brownian motion and photoelectric photon theory of light basically. And the Nobel Committee chose this last part, the contribution of Einstein in explaining this photoelectric effect. So we are in that, we are completing 100 years of that Nobel Prize, and this is a good time to talk about what is this photoelectric effect that brings Nobel Prize to Einstein, and which supersedes relativity, which is so dramatic and so revolutionary, which changes the entire concept of space and time. And that work was also there in 1905, and this photon theory of light explaining photoelectric effect was also there in 1905. And the Nobel Committee mentions about relativity and all those things in the presentation speech, but then says that no, this photon theory is something very, very special, and this explaining photoelectric effect has big consequences, and awards Nobel Prize to Einstein. Okay, this whole idea of celebrating this centenary year of Einstein getting Nobel Prize is from Indian Association of Physics Teachers, the branch of it, National Anveshika Network of India, for which I am the coordinator, national coordinator. We have 26 labs running under this umbrella in India, and all those in charges of 26 Anveshikas are doing something or other on photoelectric effect to tell these stories and to make aware of how the experimentalists have done wonderful experiments to bring out this photoelectric effect, and how Einstein has come out with the explanations and all that. So that's the background of this course. And if I go into the story, we will go into the story, but before that, let me tell you, there's yet another very special thing about photoelectric effect. It has contributed in 3 Nobel Prizes. Not only Einstein, but 2 more Nobel Prizes this photoelectric effect has contributed in that, and those are one to Philip Lenard, and in 1905 Nobel Prize in Physics is to Lenard. I will just read from presentation speech. Although the prize is basically for doing experiments with cathode rays, which are nothing but the stream of particles emitted by some material, and Lenard had done a wonderful thing that I will tell in more detail. But Leonard's Nobel presentation speech also mentions the work Leonard had done on this photoelectric effect. Einstein is there, and the third one is Robert Millikan. We all, many of us know Millikan's oil drop experiments. Many of us who are teachers, who have done MSc, BSc, MSc, they might have done this experiment also, where the determination of a charge on electron, that's the goal of that experiment, is very famous. Millikan is for that. But he gets Nobel Prize for all the studies, but very specifically a good contribution in that is from the experiments Millikan had designed, conceived and implemented and performed, and results obtained on photoelectric effect. Okay, so let me read some sentences from the presentation speech of these 3 Nobel Prizes where photoelectric effect has some contribution. So here I am reading from awards ceremony speech, Nobel Prize 1905. This is Nobel Prize 1905, and it is given to Dr. Philip Leonard, professor at University of Kiel, for his important work on cathode rays. Now, this is 1905, and photoelectric effect experiments by Leonard's were say from 1899 onwards. So it was not, it was very recent at that time. So focus on these sentences here. In his more recent work, Leonard has been able to produce cathode rays with relatively slow speed, rays which are formed through, cathode rays are just electrons. At that time, cathode rays was more popular name, which are formed through the influence of ultraviolet light on bodies charged with negative electricity. This has also served to explain an important phenomenon noted by other research workers. So this is the Nobel Prize presentation speech for this Philip Leonard. And then let me tell you at the 3rd Nobel Prize, which is this. This is Nobel Prize in Physics 1923. And this was given to the Royal Academy of Sciences, awarded this year's Nobel Prize of Physics to Dr. Robert Andrews Millikan for his work on elementary charge of electricity and on the photoelectric effect. I will tell in much more detail what Millikan had done, what kind of experiments he has performed on photoelectric effect, which has earned him this Nobel Prize. Now, the first thing I should do is what this photoelectric effect is all about. There may be some friends participating in this story session who have not gone through photoelectric effect formally, because that is being taught in our nation in class 12, and that too at the end of class 12. So the students who have passed class 12, they of course know what photoelectric effect is. But if there are students who have not gone through that, very simple, light when falls on certain substances, and photoelectric effect name is specially commonly taken for metals. When light falls on metals, in certain situations, this light is able to eject some electrons from that metal, and this phenomenon is known as photoelectric effect. Now in 2021, there's so much of technology, there's so much of instruments and so much of knowledge about the structure of the material and all that, that it seems very trivial thing. That okay, light falls on a metal and some electrons absorb energy from that light and they come out of metal. Very trivial thing. But the way in which scientists have reached this conclusion or have seen these things in action, that story is really very, very important. Okay, so today I'll just go through the very early developments in electricity and magnetism, and I have put some names here that you can see. Early heroes of electricity magnetism. So maybe what is available, what is documented, what is known to us, only we can talk of this. There may be many heroes who might have done wonderful things in this area, but somehow at least I do not know them, and therefore I am not listing. So this is no way a comprehensive or a big list or a complete list. There may be many scientists, and in fact I have chosen only few. Even from those who are known, whose work are documented, it's so vast that I cannot go into each of them. So I have chosen some landmark contributions. So Gilbert, this is 1600, around 1600. He writes a book in Latin, which is the title, the name, the English translation would be On the Magnet. So before that, people only knew that, as it is known today, people only knew that there are charges of opposite kinds. If you rub one material on other, amber, especially on some fur, and then they get properties of attracting small material particles like paper pieces and all those. So that was known about the electricity. And magnet, there are some natural lodestones which have this property of attracting iron things. So that was. But then Gilbert made a lot of studies, and then all his findings he write in this book on the magnet. Benjamin Franklin is a very well-known name, and his kite experiment is very famous, and this was conducted sometimes in middle 18th century, some around 1750s. He had done a lot of work, and the famous kite experiment for which Benjamin Franklin is known very widely, it's a general knowledge now, not only physics students and teachers, that the thing which happens in clouds, that lightning, and the things which are done in our laboratories on this charged electricity, they are same. So there also the same electricity is there in clouds, which is there in the laboratory on which the experiments were going on very fiercely during those times. So that and it was very risky experiment also, because so much of storm and so much of rain, and in that he performed the experiment with his son, and so on. Then Coulomb's law. Coulomb's law, everyone knows what is Coulomb's law, Q1, Q2 by 4 pi epsilon naught R square. So this Coulomb, this time is also, say, middle 18th century, where he formulates that, okay, if we have two charges separated by some distance, then the force is proportional to Q1, Q2 by R square, that is known as Coulomb's law. So that is this timeline. Then this Galvani, this 1786, he did some frog muscles twitching using spark from some electrostatic machine which were developed by that time by different innovators, inventors, scientists who were there to study electricity, what electricity is, and how to make useful applications of that. Then Oersted, very respected name, Oersted, he connects this electricity to magnetism. Okay, the magnets were there, and studies on magnets were going on, and all those things. And on the other side, electricity, current electricity, those things were going on. And Oersted connects through his experiments that the charge flow the electric charges, and that affects compass. So just like a magnet affects compass, the electric current also, current carrying wire also affects compass, and therefore electricity and magnetism are related phenomena. So that comes from Oersted. Then Ampere, we know Ampere's law, Ampere's circuitous law, and the unit of current is ampere in honor of this person. Then Ohms, then Faraday, Henry. These are very big names who have done a lot of experiments, and based on those experiments they have formulated laws like Coulomb's law, right? Faraday's law and Ampere's law and all those things that are there. So these kinds of experiments separately on electricity, separately on magnetism, and then combined electricity and magnetism. Faraday's law of electromagnetic induction, we all know. So those kind of things were done. And then comes the superstar. And that superstar is James Clerk Maxwell. He writes some articles, some papers, and there he writes number of equations, a number of differential equations, okay, all kinds of calculus, differential calculus is there. And the best thing is that from those equations, from that mathematics, he predicts that there should be electromagnetic waves. If you do proper experimentation, electromagnetic waves should exist. So that came from his equations, and in the original paper there are some 14 or 16 such equations, but then later people have arranged them in a nice way in vector form, and now we know the entire electricity magnetism can be clubbed in 4 Maxwell's equations. Okay, and so that is a theory. He has developed a wonderful theory which combines electricity, magnetism, and predicts that there should be an electromagnetic wave. And not only that, he predicts that there should be an electromagnetic wave, he calculates from the theory what should be the speed of that electromagnetic wave. If you do something, you make a circuit and then do something, maybe from your setup, waves will be generated. What kind of wave? Electric field and magnetic field. They will be changing with time and space. So that wave will propagate. And what will be the velocity, speed of that wave when it propagates in empty space or in air? Calculations from those equations give that it should be somewhere around 3 into 10 power 8 meter per second. And a totally separate set of physicists, scientists who were working with light, a lot of research on light, and there's a wonderful story of measuring the speed of light, how people have gone through various exercises and finally gotten the speed of light as 3 into 10 to power 8 meter per second. So that was independently known, and this Maxwell's equations tell that okay, the electromagnetic wave should be there, and if they are there, they should move with this velocity. And immediately light was also clubbed with electricity and magnetism. So with this background, next lecture I will be coming to some experiments where this electromagnetic wave was created by Heinrich Hertz. I'll be talking about that, which will relate to photoelectric effect.